session on concurrency. It's my pleasure to be chair of this session. I'm Alistair Donaldson from Imperial College London and Google. We're going to have three presentations. Two are going to be related to memory consistency models, and one is going to be related to benchmarking. And the first presentation is entitled Promising ARM RISC-V, a simpler and faster operational concurrency model. And the presentation will be given by Christopher. Take it away.
Yeah, thank you. Sound okay? So this is joint work with Jean Pichon, Ji-Hoon Kang, Sang-Wan Lee, and Chung-Kil Huo. Right. Concurrency programming is known to be hard, and one reason for this in practice is that widely used programming languages like C or Java and processor architectures like x86 or ARM have so-called relaxed memory models. And that means they only give weaker guarantees about the concurrency behavior and make programming more difficult. And to illustrate this, on the left you can see an example of a tiny concurrent data structure for message passing between a producer and a consumer thread. The producer thread does some computation and writes the result to the shared location D, and then sets the flag F to let other threads know the data is now available. The consumer thread is running in parallel in this loop, waiting for the flag to be set. And once it sees the flag set to 1, it breaks out of the loop and reads D and returns the value. Now here we made the producer thread always write 42 to D, and so we'd expect the consumer thread to also always return D equals 42. But if we wrote this program in C and compiled it to ARM, for example, another possible outcome would be the consumer returning D equals 0. And the reason is the relaxed memory behavior. And in particular, so there's two different explanations. First, on the producer thread, there's these two writes here, and they're unordered. And that means the producer could do the second one first, so that the consumer would see the flag set to 1 before the data has even been written. And the second explanation is the consumer thread. So there's this control flow dependency from reading the flag set to 1 to breaking out of the loop and reading D. But the hardware might do speculative execution and effectively execute this load of D before the load of F, and again cause the consumer to return D equals 0. So then it's up to the programmer to understand the ordering requirements of this program and maybe put in some explicit ordering. Here maybe in the form of release acquire annotations to prevent this sort of bad behavior. But the problem is that the typical kind of testing would not have revealed this bug because many of these relaxed memory outcomes only show up a couple of times in a million runs and maybe only on particular hardware. Right, and so this is infeasible to do by testing, and so instead what's required is a precise semantics of the concurrency behavior, and ideally that also be tool support for detecting those kinds of bugs. And so here we're trying to address this for ARMv8 and RISC-V. Now from our previous work on ARMv8 concurrency, two concurrency models already exist, and there's corresponding ones for RISC-V. There's the official reference model. This is an axiomatic model, and that means it gives you a specification of the concurrency behavior in terms of global axioms of completed executions, and this gives you an abstract and concise specification, but it means it does not work incrementally. You can't understand it in terms of step-by-step execution. And the second model that exists is the flat operational model. So this is an abstract machine model with states and transitions, so you can incrementally execute it. This model has been proved equivalent to the axiomatic model, and this model has a closer relation to hardware, which has been very useful in engaging with ARM and establishing the precise semantics, but it also leads to some complexity that just for this purpose would be good to avoid. And so here we're presenting this new model called Promising ARM RISC-V, which is a model based on the ideas of the promising semantics for C11 concurrency, but here applied to architectural models. And what you get with this is an operational model that computes incrementally. It's much simpler, we think, than the flat operational model. We've proved this model equivalent to the axiomatic models for ARM and RISC-V in COG, and on top of it we've built an executable tool that you can use for checking the correctness of concurrent data structures. Right, and so now I'll briefly give an overview of the sort of three main ideas this model is based on. First idea, the out-of-order execution of reads that the architecture allows is explained by allowing reads to read from older writes in the message history. If you look at this program now, this is the same message passing program as you saw before, just now what it might look like when compiled to some sort of toy assembly language, although the later tool will handle the real ISO model. The interesting execution was the one where thread 2, which is the consumer thread, read D equals 0, And one of the explanations was that it could execute this load of D out of order before the load of F. And the model explains that as follows. If you look at the part below, that shows you parts of the operational model state. And it has a sort of standard register state for each thread and a memory state. And the memory state is just a list of all the write messages the model has seen so far. Initially just with one initial write setting everything to 0. Now if we just go and step through and do the store of D equals 42, then this just adds a write message to this message history. And same if we do the store of F equals 1, this adds another write message to the message history. And if we now do the load of F, well, any load can always read from the most recent write to its address in memory. And if we do that and read from this write of F equals 1, this sets the register state for R1 to 1, so that in the next step the condition evaluates to true, and we can execute the load of D. This load could again now read from the most recent write to D, but loads are also allowed to read from certain older writes in the message history. And in particular, this load could now also read from the initial write of D equals 0. And if we do that, this sets the register state to 0 and gives us this sort of interesting outcome. Now, allowing loads to read from arbitrarily old writes would be too liberal a semantics. And both ARM and RISC-V put some constraints on this. And this could be constraints coming from memory barriers in the program or from data flow dependencies. And here we're looking at the latter, where if you look at the program, it's the same program as before, just now tweaked so that the load of D has a syntactic address dependency on the load of F, whereby the expression computing the address involves the return value of the load of F. And this syntactic dependency alone is enough to architecturally guarantee that this load of D has to effectively happen after the load of F in ARM and RISC-V. And the model handles that with a concept called views, which I'll explain in a second. So we just go to the state after we've done thread 1 and before we've done thread 2, then the memory state was the one you see below. But what hasn't been shown yet is that actually whenever a write goes into memory, the write receives what's called a timestamp. And the timestamp is just the index of this write message in memory. So we have D equals 42 at timestamp 1 and F equals 1 at timestamp 2. And now a view is simply a timestamp which sort of captures the intuition that a certain thread has seen a certain write. And in particular, the register state for handling dependencies contains a view for each register. So if we now execute this load of F on thread 2 and again read from this write of F equals 1 at timestamp 2, then this sets the register state to R1 as before. But what it also does is it annotates this register with a view, the view 2, which records the fact that we just read this write at timestamp 2. And this will constrain future loads and stores, intuitively sort of capturing the idea that anything dependent on register R1 has to have seen the write at timestamp 2 and any write leading up to that point. So now the next step, again, the condition evaluates to true. And now, because this load of D syntactically depends on register R1, it's constrained by the view 2, and this will prevent it from reading this initial write, because at timestamp 2, the initial write has been overwritten by this more recent write of D equals 42 at timestamp 1. So now it's forced to read this more recent write, and this prevents the previous outcome. But then, sticking with exactly the same program, while the syntactic dependency from the load of F to the load of D prevents the out-of-order execution and this early execution of the load of D, the interesting outcome where the consumer thread returns D equals 0 is still allowed. And that's because thread 1 could also execute these two stores out of order, F equals 1 before D equals 42. And the model handles that with a concept called promises, where a promise here is a promise of a write message. And the idea is that at any point in time, so in any operational model state, a thread can make a promise of any write message at all, provided it can later fulfill this write. And in particular, in the initial state, thread 1, instead of doing the store of D equals 42, could also start by promising this write of F equals 1 if it can later fulfill this. So if we just go ahead and try this, doing this promise adds this write message of F equals 1 to the message history. And then, for any thread other than thread 1, this write is just like any other, except that for thread 1, it comes with the additional obligation of having to later fulfill this promise. which we record in this promise set in the thread state. So now in the next step, we could again do the store of d equals 42, which adds it at the end of the message history. And now because in the next step, we can do a store of f equals 1 that matches this outstanding promise, we can fulfill the promise. And fulfilling the promise means we don't add another message to the message history, but just eliminate this outstanding promise that we just fulfilled. And now if you compare this memory state to the one you saw before, then this has the write of f equals 1 and the write of d equals 42 in reversed order in this message history. And this will mean if we execute thread 2, although I'll sort of skip over the details now, this will mean the views on thread 2 will work out in a way that allows it to read d equals 0 again, giving us this sort of interesting outcome. Right, so that's sort of the three main ideas the model is based on. And then the full model has a bunch more detail to handle all the architectural features, which you can read about in the paper. Now on top of this, we've built this executable tool. And here we're building on a bunch of existing work on user mode ISO models for ARMv8 and RISC-V written in the SAIL specification language, and also infrastructure for operational relaxed memory concurrency models. So on top of this, we're building this executable tool for checking the correctness of concurrent ARMv8 or RISC-V assembly programs. And the way you would work with this tool is as follows. You take your program compiled to assembly code. You use our existing script to map it into the format that the tool targets. And then you can run the tool in an exhaustive mode, which computes the set of all possible final states allowed by the model for this program for loop-bounded executions. And so you get this list of possible final states, and then you can go and check, maybe manually, maybe with some other script, to see if any of these executions corresponds to some bug in your program. And then what the tool gives you in addition to that is if there's a surprising outcome in these final states, you get a witnessing trace for each such state, and then you can go and put this witnessing trace back into the model and run the model in an interactive mode, where you can then sort of interactively replay and step through this execution to see how this execution works and where things go wrong, to hopefully sort of debug what's going on. Right, and so to make this exhaustive computation fast enough to handle some interesting examples, we're using two main optimizations. The first one is an interesting property of the model that we proved in Coq, which is that if you have a given execution, there's an equivalent execution that does all the writes, all the promises of that transition first. All the promises of that trace first. So if you have a trace tr, then there's an equivalent trace tr prime, which has this shape. It starts with a sequence of only promise transitions, and then followed by a sequence of only non-promise transitions. And that means if we constrain this exhaustive mode to only search for paths of this shape, this cuts down the non-determinism. And then the second optimization is based on the observation that if you're following a path of this shape, and once you've reached a state where you've stopped promising, so where you're in this non-promise mode, because now you're not doing any new writes anymore, the memory is essentially fixed, and you can now explore the possible set of final thread states for each thread under this memory, basically in parallel, because there's no interaction between the threads anymore. And this again speeds things up. Right. Now, to sort of validate the performance, we ran a whole bunch of examples, and these are sort of standard textbook concurrent data structure examples and lock implementation examples. We wrote the code for these in C++ or in Rust, together with some sort of test code to sort of log what's going on and detect buggy executions. We then compile this with GCC or LVM optimization level 3 to ARMv8 assembly, and use a script to map it into this litmus format that the tool targets, and run the model in exhaustive mode to get the list of all possible final states. And we do the same for promising, for the flat model, and for the axiomatic model to compare the performance. We ran this on a bunch of examples, which I won't name individually, but the sort of biggest ones we've tried are the chase left DQ example, where you can see the C++ source code in the background and the Michael and Scott queue. And we've collected the performance numbers, which again, you can see the full performance numbers in the paper. But the numbers show that the promising model is much faster than both flat and the axiomatic model for the tests we've run, and scales much better than them. But the main point really is that with these numbers, it's sort of fast enough that you can maybe usefully, well, you can use it for some interesting examples already. Right. And I think I'm finishing a bit early. So to conclude, we've presented this promising ARM RISC-V model, which is an operational concurrency model for ARMv8 and RISC-V that we think is much simpler than the flat model. And maybe this step-by-step execution makes it also simpler than the axiomatic model. On top of it, we've built this tool, executable tool that you can use for exhaustively computing the outcomes for loop-bounded instances of concurrent data structure examples and interactively debug. And we've got some interesting early performance results, although we want to also see whether we can use known existing model checking techniques to get better performance numbers and maybe get closer to the sorts of state-of-the-art results for stateless model checking kind of things that we'll hear about later. And if this model sounds interesting to you, then please check these links I'm giving here. The models are all available publicly online. The promising model and also the other the flat operational model are available on GitHub, as are the SAIL ISO models for ARMv8 and RISC-V and the SAIL specification language. And if you'd like to try the model without compiling, there's a graphical online web interface version that you can use to interactively and exhaustively try these examples. Thank you.
Thanks very much, Christoph, for a very nice talk. We've got plenty of time for questions, so please come up to the microphone and do say who you are before you ask your question. Thank you.
Hello, I'm Andrew Appel. If you could turn back to slide 4. So you have the artificial dependency, D plus R1 minus R1.
Yeah.
This looks a lot like the consume mode atomic of C11, which has proved very problematic in the C11 model, partly because compilers tend to optimize it away. Now, I realize you have an instruction set architecture model, not a compiler model, but a lot of the presentations of the principles of these reorderings try to be agnostic about whether it's the compiler or the implementation of the architecture that's doing these optimizations. So do you not foresee problems with the robustness of this kind of dependency?
In the sense as...
well, for the same
in
kind
the
of
case
reasons that in the C11 community, it's proved difficult to get this right.
So, in fact, I previously had a slide, and since I thought I was going to run out of time, I dropped it. But what I was going to say here was this, that sort of partly because if you're mostly interested in these concurrent data structure implementations, you might want to have a tool that works at the language level. One reason we're looking at this architectural level is that these questions are simpler there. The question of dependencies gets simpler. So of course you might end up compiling the program and find that the compiler removes some dependencies you wanted your code to depend on. But in some sense that's part of what makes it attractive to target this, is that people do this in practice where they sort of bypass the C11 language specification because they do want to rely on these dependencies, although the language spec doesn't guarantee it to them. But then well, the sort of machine code you get out is the final truth, and if that ends up preserving your dependencies, then that's good enough for some people. So this is something the tool handles. But
thank you.
Don't know if that answers the question.
Hans from Google. You had the example where you said D to 42 and then sort of flag to 1. Well, it doesn't matter, just any two stores in a row. Do you handle the case with where you promise the store to F and then the store to D trapped, and the code does something else? Can you handle that somehow in this model?
So the ISO model we're handling so far is the user mode ISO, and this doesn't deal with exceptions yet, with interrupts in the hardware. There is a bit of that in there, in that one ordering you get, for example, from loads to stars, if the load feeds into an address of a memory access preceding a star, so you might get a page fault or something, this could cause an interrupt, and then because of the preciseness of exceptions, you're guaranteed that the star has to happen after those dependencies have been resolved. So a bit of that shows up in the model already, even though it's only dealing with that user mode stuff. But so I guess an extended version of the model would have to take care of regarding these sorts of things as dependencies, that you have to wait until you can guarantee there's not going to be any exceptions anymore once you're promising the star.
Thanks.
We'll take one more question, but could the next speaker start to set up in the meantime, please?
So I can see how I could use this tool to model check and see the outcomes of small pieces of code. How can I build on top of this to build a logic to prove big pieces of code? What are your thoughts on that?
That's a good question. We're looking at that at the moment. So there's been a program logic for the promising model for C11 concurrency. So this might be instructive in building one for this model. But yeah, we're in the process of working on one. We'd be interested in talking about that, but yeah.
Okay, thank you.